Good morning all. So today we are going to discuss few numericals regarding the transmission line, what we have discussed in the previous class. Depend upon the input impedance, how we are calculating input impedance, then VSWR, reflection coefficient, whatever the parameters we have identified in the previous class. Now we are dealing with the questions, and one by one I will solve it and it will be helpful for you. Okay. So I have took one question. You can see that a transmission line whose length is 10 centimeter, okay, and operating at a frequency which has phase constant beta is 30 per meter, okay, and wavelength is of 40 centimeter. Find the electrical length of the line. Now when this electrical length will come, last class I have discussed, when we are calculating input impedance, okay, input impedance for a line, Zin is equals to Z0 whole into ZL plus Z0 tan hyperbolic gamma L divided by Z0 ZL tan hyperbolic gamma L. This is for lossy case, okay. But if it is considered for lossless line, okay, then our input impedance reduced to ZL plus J Z0 tan beta L divided by Z0 JZL tan beta L. Okay, so like this we can represent. Now what I have told, this product beta L is called as electrical displacement, okay, electrical displacement. So beta L. So here in this question it was asked that you have to determine the electrical displacement. So electrical length or electrical displacement both are same. So here I will write what are the given data. Length of the line is 10 centimeter. So 10 by 100, so it is 0.1 meter. Then phase constant beta is equals to 30 per meter. Now beta is equals to this, length is equals to this, and wavelength is given as 40 divided by 100, that is 0.4 meter. Okay. Now our electrical displacement is what? LE is equals to beta into L. Now what is beta? Beta is 30. What is L? It is 0.1. So that means it is 3 meter. Beta into L, so L constant, so we will get beta L is equals to 3. Now this actually this beta is represented with terms of radian. So this length, electrical displacement, is nothing but an angle. So here 3 you have to represent in terms of angle. So it is 180 degree divided by pi. So you will get around 171.9 degree. So this is my electrical displacement. Okay. So this is called as my electrical displacement. Done. So with the help of this small relation, you people can identify the electrical displacement. So one more question we will take. Okay. So this is one more question. So as I have written, a transmission line has a following parameters, that is R, L, G and C, whose values is 100 ohm per meter, 80 nanohenry per meter, then conductance is 1.6 Siemens per meter, and capacitance is 200 picofarad per meter. Consider the traveling wave on the transmission line operating at 2 GHz. That means the wave which is propagating in the transmission line is of 2 GHz. And with the help of this data, we have to calculate what is alpha, what is beta, what is phase velocity, what is characteristics impedance, and what is group velocity. Okay. Now, one by one we will identify how to determine this propagation constant, and with the help of that propagation constant, how we can determine this alpha, beta, and gamma. So the simple relation is, first we will identify the relations. So it is R plus j omega L and G plus j omega C. And one more important thing, since all the RLGC parameter is given, that means this line I cannot consider as a lossless line. Rather than this line is called as a lossy line, in which all RLGC parameter is available. Okay. So if you solve this, we will get one real value and one imaginary value. So with the help of this relation, this alpha and beta can be determined. Similarly, this is the first relation. Second, in order to determine the characteristics impedance, we have a relation R plus j omega L divided by G plus j omega C. Now what is the value of omega? The value of omega is 2 pi f. So it is 3.14. F is 2 gigahertz. 2 into 10 to the power 9. This is radian per second. Omega, angular frequency. So whatever the value you will get, substitute here, solve this value, you will get your characteristics impedance. Similarly, propagation constant, if you solve it, it is a complex term. Real part you will get and imaginary part. Real part is called as attenuation constant and imaginary part is called as our phase constant. Okay. And what is about phase velocity? So once all these things are known, phase velocity is omega by beta. Simple, small relation. Now what is beta term? Either you can take from this particular equation, or beta is equals to omega root over of LC, or here I will write directly root over of LC. If you take this value also, same result you will get, and if you take this LC component also, same result you will get. Then fourth one, Z0 we have calculated, phase velocity calculated, and group velocity. Now what is group velocity? Now group velocity into phase velocity is the square term of your speed of light. So that means group velocity is c square divided by phase velocity. So with the help of this relation, we can easily determine this value. Let's see. So first I am going to calculate propagation constant. So propagation constant is R plus j omega L and G plus j omega C. Now whatever the value of R, that is 100, L is 80 nanohenry, G is 1.6 and C is 200 picofarad, and omega value is 2 into 3.14 into 2 into 10 to the power 9 radian per second. Substitute all those values in this and try to solve it. If you solve this value, you will get around 17.94 plus J 5.185. So this is the constant value you will get after solving the above relation. Now here the real value is 17.94 and the imaginary value is 5.185. So this is nothing but attenuation constant Nepper per meter, and this one is radian per meter. So alpha and beta we have determined. So A is alpha and B is beta. Next we have to calculate what is our phase velocity. So phase velocity is omega by beta. What is the value of omega? Omega is 2 into 3.14 into 2 into 10 to the power 9 whole divided by beta 5.185. If you solve this, your phase velocity we will get around 2.42 into 10 to the power 8 meter per second. So this is my phase velocity. Then, or with the help of 1 by root over of LC also you can put L and C value, you will get the same value. Okay. Next, what is our characteristics impedance? Characteristics impedance, we will use this relation. So it is R plus J omega L G plus J omega C. Substitute all this value, R value, L value, G value, C value, and as well as our omega value. So if you solve this, you will get your Z0 will be around 17.9 plus J 4.3 ohm. So your characteristics impedance is 17.9 plus J 4.3 ohm. So this is your characteristics impedance. And what we have left with phase velocity, groove velocity. So groove velocity with the help of this relation c square by Vp. Now what is Vp? Vp is 2.42. So it is 3 into 10 to the power 8 whole square divided by 2.42 into 10 to the power 8. So here I will get 9 into 10 to the power, this is 16, this is minus 8 divided by 2.42. So 9 divided by 2.42 into 10 to the power 8 meter per second. So 2.42 means your groove velocity will become 2.563 into 10 to the power 8 meter per second. So this is my groove velocity. So similarly, the groove velocity, if it is given, you can easily determine the phase velocity with the help of these relations. So using this relation, we have calculated the unknown factor with the help of the known quantity. Okay. So this is one sort of question. One more question we will take. Okay. So this is one more question. Here I have written, a transmission line has an attenuation of 10 dB per meter. Now basically the attenuation factors are measured with Nepper per meter. Now it is given in terms of dB per meter. So there is a relation with dB and Nepper, that 1 Nepper is equals to 0.1151 dB. I have written here. This is the basic relation. Remember this. Either the question will be given in terms of dB or in terms of Nepper. So 1 Nepper is equals to 0.1151 dB. So, and the phase constant is 50 radian per meter, and the wave which is propagating in the transmission line is 2 gigahertz. Okay, is 2 gigahertz, and here we have to calculate what is propagation constant gamma for the transmission line. That is the first part. And the second, the condition is given, if C is equals to 100 picofarad and the conductive loss G is equals to 0, then what will be my characteristics impedance? Okay, so these are the two factors we need to calculate. It is a very simple one. Let's see how to proceed. So first of all, you have to convert the alpha value which is in dB per meter into Nepper per meter. Okay, so alpha Nepper per meter is equals to 0.1151 into 10. Okay, is it fine? So let me check once. Okay, so this is into dB. Okay, so it will be 1.151 Nepper per meter. So this 1.151 Nepper per meter is the alpha value. Similarly, beta is equals to how much? 50 rad per meter. Done. So what will be my propagation constant? Propagation constant is alpha plus j beta. Alpha is 1.51 plus j 50. So gamma value is 1.151 plus j 50. Okay, so this is my propagation constant. Done. Then B. If C is equals to 100 picofarad and conductive loss capital G is equals to 0, so what will be my characteristics impedance? Now the characteristics impedance, we have a relation R plus j omega L divided by G j omega C. Even this relation can be written as gamma divided by G plus j omega C. Simple. Now with the help of this condition, conductive loss capital G is 0. So if capital G is 0, here I will write at capital G is equals to 0. So gamma divided by omega C. So what is my gamma value? 1.51 plus J50 divided by J. Omega value is 2 pi f into capital C is how much? 100 picofarad, 10 to the power minus 12. Now it is a simple complex division. Solve this, you will get around 39.8 minus j 0.916 ohm. So this will be my characteristics impedance. 39.8 minus j 0.916, this much ohm. It is a simple one. So you need to remember the relations. You need to remember what are the formulas behind it. If you substitute here directly, we don't know what is the value of R. So there is again it is an unknown factor. But if you substitute in this relation, having the same values, gamma divided by G plus j omega C, the values are known. And here the G value it is terms as 0. Conductive losses tends to 0. So if it is 0, that means directly we can find out the values and we can identify the resultant. So here Z0 is 39.8 minus J 0.916 ohm. And here it is propagation constant, as we have identified. Nepper is need to be converted into dB. If dB is given, multiply this value, you will get as a Nepper quantity. Okay. So this is one sort of example. One more example we will take. Okay. So this is one more question. Here I have written a certain transmission line of 2 meter, means length of the line is 2 meter, operating at a frequency of 10 to the power 6 radian per second, and with attenuation constant 0.921 Nepper per meter, and beta value is 1 rad per meter. Okay, and characteristics impedance is 60 plus J40 is given. If the line is connected to a source, means generator potential is given 10 angle 0 degree, with generator side input impedance is 40 ohm and transmitted by a load of 20 plus J50 ohm at the load term. We have to determine the input impedance, we have to determine the sending current I will show, and we have to determine the current at the middle of the line. Okay. So let us consider this is the 2-wire line whose length is 2 meter. Okay, whose length is 2 meter. Here ZG is connected at the input side with a generator's part, that is called VG. This is plus minus V0. Current is I0, and input impedance we can measure at z is equals to 0 and z is equals to 2, and the load is connected here. It is ZL. So here the current is IL plus minus this is VL. So this is the figure. ZG is present and VG is present. VG is how much? 10 angle 0 volt. How much is ZG? ZG is 40 ohm. So according to this figure we need to proceed. Okay. So first of all, what are the given data? We will see. The length of the line is 2 meter. Operating angular frequency is 10 to the power 6 rad per second. Done. Alpha is equals to 0.921 Nepper per meter. Beta is equals to 1 rad per meter. And Z0 is equals to 60 plus J40 ohm. This is the characteristics impedance which remain constant throughout the line. Next, if the line is connected to the source, so this is the source and the transmitter to the load is 20 plus J50 ohm, ZL. Done. We have to find out what is the input impedance, what is the sending current, and what is the current at the middle point. Okay. So, as you can see that alpha value is known, beta value is known, that means which sort of line it is? This line is called as a lossy line. Okay. Here it is not a lossless line. Lossless line means your alpha terms will be 0. But here alpha is there. We cannot ignore the presence of alpha. So alpha value we have to include. So my gamma value is alpha plus j beta. Alpha is how much? 0.921 plus j beta is how much? 1. So gamma is equals to this much. Now what is our input impedance formula? Input impedance is Z0, ZL, Z0, 10 hyperbolic gamma L, Z0, ZL, 10 hyperbolic gamma L. This is the simple relation. Okay. Now here input impedance we have to calculate ZE, and for this particular value, what is the ZL value? ZL is this much, 20 plus J50. Okay. Gamma value is this much. Gamma into L means how much? Gamma into L means it is 0.921 plus J whole into 2 meter. So here we will get 2, 4, 8, 1.842 plus J2. So this is the gamma L value. Convert into polar form. Take the 10 hyperbolic of this component. Substitute here. Z0 value is given how much? Z0 is 60 plus J40. Substitute the value. ZL is how much? 20 plus J50. Substitute this value. Solve this input impedance value. After substituting each and every component, you will get input impedance is around 60.25 plus J 38.79 ohm. So input impedance is 60.25 plus J 38.79 ohm. So this is the input impedance calculation. Okay, this is the input impedance calculation. General relation. First of all, you have to identify which sort of line it is. My line is lossy line. How? Because alpha term is there. If alpha is 0 means you can consider it is a lossless line. Done. Next. So this is the input impedance calculation. Next one is the sending current. Sending current means I0 we have to calculate. How to identify this I0? Let's see. For that I am using a figure which we have discussed earlier, how we are determining the input I0 current. Okay, this is plus minus Vg, this is Zg, and this impedance is Zd, what we have calculated. Done. So this is my Zin. V naught is the potential drop across this, and here the sending current is I naught. Okay, this is the loop. But how to determine this current? Current formula is what? Potential by impedance in that loop. So what is the total impedance? Zin plus Zg, and what is the source? Vg. So that means I naught is equals to Vg divided by Zg plus Zin. So Vg is known 10, Zg is known how much? Zg is 40 ohm, and what is input impedance? 60.25 plus J 38 plus 79. So if I will substitute all these values, let me erase this part. So my sending current I naught is 10 divided by 40 plus 60.25 plus J 38.79, which is this Zin. If you solve this, you will get around 93.05 angle minus 21.5 ampere. So this is my sending current. Sending current means this I naught. Always remember this. Okay. Next we have to calculate the current at the middle of the line. Now how to calculate the middle of the line? For that we have a relation Is of Z. Most probably you people have known about it, how to calculate this current at the mid part. As we know, Is of Z is equals to I naught plus e to the power minus gamma Z plus I naught minus e to the power plus gamma Z. Okay. Now here Z is equals to 2 because the total length is 2, and here we have to calculate at the middle of the line. Middle of the line means at a distance 1 meter. So what I will do, here I will write V naught plus divided by Z naught e to the power minus gamma, because Z becomes 1. Here I will write Is at Z is equals to 1 minus V naught minus divided by Z naught e to the power plus gamma over Z value is 1, half of the distance. Now here most important thing is what? Here we have to calculate what is incident potential and what is reflected potential. We have that relation. Only that relation will help us to find out these values. So let me write that relation once again. So first I naught we have calculated 93.5 0.5 minus 21 15 degree ampere. Similarly V naught I can identify I naught into Zin. So it is 93.05 21.5 into Zin. Zin is how much? Zin we have calculated as 60.25 plus J plus J 38.79. So if you solve this, your V naught you will get around 6.667 angle 11.62 degree volt. So this is my V naught, this is my I naught. So now V naught plus and V naught minus we have to identify. So V naught plus relation is how much? Half V naught plus Z naught into I naught, okay, and V naught minus is half V naught minus Z naught into I naught, okay. So these are the two values. After determining this incident voltage and reflected potential, substitute in this equation. You will get your current at midpoint, because total Z is 2, middle point means Z is equals to 1. So if you solve this, V naught, I naught, Z naught, whatever is given, substitute here, you will get V naught as 6.687 12.08 degree, okay, and V naught minus is 0.0518 angle 26 degree. So these are the two potential. Substitute these two potential in these two equations. E to the power minus gamma, gamma value is given, e to the power, take the exponential part, V naught plus divided by Z naught. So whatever the V naught is given divided by Z naught. After substitution, your current you will get around 35.10 angle 281 angle milliampere. So IS at midpoint is 35.10 angle 281 degree milliampere. Okay, so this is a simple calculation, but some relations need to be memorized, some relation need to be identified, and those relation will help you to determine the current. Okay, so this is the simple relation through which we can identify all our parameters as asked in this particular question. Okay, we will proceed to one more question. Okay, so this is one more question, fifth question. So a lossless line, it was already defined, okay, with a capacitance of 200 picofarad and inductance is 0.5 microhenry per meter, which is excited with a sinusoidal source of a frequency of 1 kHz, means operating frequency is given as 1 kHz. The magnitude of the volt measured across 35 ohm, which is a load, is 100 volt. That means indirectly it is given as VL. Load potential is 100 ohm. Okay, load potential VL, because ZL is given as 35 ohm. Here we have to calculate what is the characteristics impedance, reflection coefficient, phase velocity, wavelength, reflected and incident potential, and the phase constant. So it is a simple one, it is a formula based. So since it is a lossless line, our characteristics impedance will have Z0 is equals to root over of L by C. So in place of L, substitute 0.5 10 to the power minus 6. In place of C, 200 into 10 to the power minus 12. Solve this. You will get the characteristics impedance near about 50 ohm. Done. So this is the first one. Second, what is the reflection coefficient at load? Now reflection coefficient at load is ZL minus Z0, ZL plus Z0. So ZL is 35 ohm minus 50, 35 plus 50. So reflection coefficient near about minus 0.1765 we will get. Done. Then what is my phase velocity? Phase velocity is 1 by root over of LC. So L value is known, C value is known, substitute in this. So phase velocity you will get around 10 to the power 8 meter per second, or 0.33 times of C. C means speed of light. Okay. Then wavelength. wavelength is CVP by F. So C by F, or it is now it is the phase velocity. So it is 10 to the power 8 and F is 10 to the power 3 because it is 1 kilohertz. So it is 10 to the power 5 meter. That is called lambda. Done. Now what is my V naught plus and V naught minus? Simple. So V naught minus and V naught plus is calculated at load terminal. Done. So what is our relation? Half VL plus Z naught into IL, and here half into e to the power minus gamma L. Okay, this is plus, and VL minus Z naught into IL e to the power minus gamma L. So since it is a lossless line, gamma will depend upon your what value? J omega root over of LC. This value. Calculate this value, substitute in this. VL is known, Z0 is known, and IL also you can determine, that is the load current. Load current is how much? IL is equals to VL by ZL, that is called your IL. You can substitute in that, and you can easily determine what is the incident and what is the reflected potential. So if you solve this, your V naught plus value will become 121.43 e to the power j beta L, and V naught minus you will get 21.43 e to the power minus beta L. So these are the two values you will get. That is our E. And what is our beta? Beta, it is a simple one. Beta is equals to how much? As the value lambda is equals to 2 pi by beta, we can say beta is equals to 2 pi by lambda. So 2 pi divided by 10 to the power 5, you will get this much beta, rad per meter. Done? Simple. So like this question will come in your exam. It is a simple thing, but it will represent in a complex manner, but the resultants all are simple in nature. Okay. One more question we'll take. Okay. So this is one more question. Simple question. A 100 ohm transmission line connected. As it is 100 ohm transmission line means it is characteristics impedance is 100 ohm. To a load consists of 50 ohm resistor is in series with 10 picofarad capacitor. You can see this figure. This is the two-wire transmission line whose length is 0.125 lambda, and load is RL is 50, CL is 10 picofarad. Okay, and with characteristics impedance is 100 ohm. Okay, now here this combinedly you have to represent what is your ZL, then only the other parameters you can calculate, because reflection coefficient at the load, it is asking means ZL minus Z0 divided by ZL plus Z0. In that relation we have to substitute. So what is ZL? ZL we have to calculate with the help of this relation. So let's see. So ZL is equals to RL minus J divided by omega CL. So this is the basic relation for the series combination of R and L. So what is my R? R is equals to 50 minus J divided by omega. Omega means it is operating at 100 megahertz. So omega is equals to 2 pi F. 2 into 3.14 into F means 10 to the power 6, and this is 8. Done. So here you substitute 2 into 3.14 into 10 to the power 8 into CL 10 picofarad, 10 to the power minus 12. Solve this, you will get your load impedance near about 50 minus J 159 ohm. So this is my ZL. Okay. So once ZL is known, next reflection coefficient at the load. So reflection coefficient at the load is ZL minus Z0 divided by ZL plus Z0. Okay. So what is my ZL? 50 minus J159. Z0 is 100 divided by 50 minus J159 plus 100. You solve this complex term, you will get around 0.76 angle minus 60.70 degree. So this is the reflection coefficient, 60.70 degree. Okay, so this is my reflection coefficient. Now once reflection coefficient is known, next he is asking about the input impedance at the input end of a transmission line if the length is 0.125 lambda. Now our input impedance relation is what? Z0 ZL plus Z0 10 hyperbolic gamma L. This is Z0 ZL 10 hyperbolic gamma L. This is the general equation. Okay. Now as it is written, a 100 ohm transmission line is connected with 50 ohm resistor and this and all. We need to identify the gamma value. Length is also known to us and we need to identify this particular value. Okay. So how to proceed this? The simple technique is, in this particular line nothing is mentioned. Okay. No information is given about the line. If there is no information is given about the line, consider it as a lossless line, because none of the parameter is known to us. Neither RLGC parameter is known, so that we can substitute the gamma value, because here it is none of the thing is given. So consider it is a lossless line. So lossless line. Okay. If none of the parameters given means consider that whole line as a lossless line. So my input impedance for lossless line, I will get Z0, this is ZL plus JZ0 10 beta L divided by Z0 JZL 10 beta L. Okay. Now what is beta? Beta is equals to 2 pi by lambda. What is length? 0.125 lambda. Multiply these two, you will get pi by 4. 45 degree you will get, that I have converted into pi by 4. So now when you will substitute here, Z0 into 10 beta, 10 pi by 4 is how much? 1. So this I will get 1. 10 beta I will get 1. So resultant is Z0 ZL plus JZ0 Z0 plus JZL. So this is my relations, what I am getting after substituting this beta L value as pi by 4. So 10 pi by 4 is 1, 10 pi by 4 is 1. So we are getting as Z0 ZL plus JZ0 divided by Z0 plus JZL. Now Z0 is given how much? 100. ZL is also given how much? It is ZL is 50 minus J 159 we have identified. Substitute those values and solve it. After substitution of this value, you will get around input impedance as 29.32 angle minus 60.70 0.65 degree ohm. So input impedance is 29.32 angle 65 ohm. So this is my input impedance. Okay. So like this we have to calculate for the unknown factor with the help of the given data. Okay. Now one more question. In place of CL I can put L also. If it is RL combination, my ZL will change. How much? RL plus JXL. XL means it is omega L. So that I have represented. So like this probability of questions may come in the exam. Okay. One more question will come take and will end up. Okay. So this is the last question for today's discussion. So as I have written, it is a lossless transmission line with characteristics impedance 50 ohm. Length is 1.5 meter is given, which is connected to the voltage source Vg with a load of ZL is equals to 50 plus J50. Okay. If Vg is 60 volt, operating frequency is 100 megahertz, Zg is 50 ohm, we have to calculate two power. One power delivered at load and one the input power. Okay. Let us consider the figure. This is our transmission line. Okay. Two wire transmission line, two conductors are there. This is the load. Okay. ZL. This is the Vg. Okay. Which is 60 volt is given. This is Zg. Zg is how much is Zg? Zg is 50 ohm. Okay. Length is 1.5 meter length, operating at a frequency of 100 megahertz, and ZL is 50 plus J50 ohm. So these are the parameters are given to us. Now first of all, power delivered at load. Power delivered at load means last class I have discussed the power delivered at load is V naught square divided by 2 Z naught whole into 1 minus reflection coefficient whole square, like this. Okay. Now here Z naught is not given. Z naught is given as 50 ohm. Let us it is given for sorry. So Z naught is 50 ohm. ZL is 50 plus J50 ohm. That means reflection coefficient can be easily calculated as ZL minus Z naught, ZL plus Z naught. So if you solve it, the numerator is J50, denominator will be 100 plus J50. If you solve this, your reflection coefficient is 0.2. Okay. So reflection coefficient will be 0.2 plus J 0.4, or in a polar form 0.45 e to the power j 1.11. So this is my reflection coefficient. Over. Next, what we have to determine? We have to determine the V naught. So what is the V naught? V naught is this potential. This is my input impedance. Okay. So let's see. So this is Zg. This is the input impedance, and this is Vg, and this current is I naught, potential drop is V naught, this is Z in, this is Zg. Okay. Now how to determine this Z in? Simple. It is a lossless line, so directly I will write ZL plus J Z0 10 beta L, then Z0 plus J ZL 10 beta L. Done. Now what is the beta value? Beta is 2 pi by lambda. What is lambda value? C by F. What is the phase velocity? Same as speed of light. What is the frequency? 100 megahertz. So lambda is 3. Then what is L? It is 1.5. So what is beta L? 3 into 1.5, that is 4.5. Substitute the value here. You will get the input impedance Zin. Okay. Now once Zin is known, I will just discuss the new steps. You people just calculate it. Okay. So after determination of beta L, substitute in this, you will get your input impedance. Okay. Now with the help of this relation, I can determine the input current I naught. Right? The sending current means input current. I naught is equals to Vg divided by Zg and Zin. So I naught is known. Okay. Next, what is V naught? V naught is nothing but I naught into Zin. Okay. So V naught is known, I naught is known. Power delivered at the load. So V naught is known means whatever the value we will get here, substitute here. Square it, divided by 2 into Z naught. Z naught is how much? 50 ohm. 1 minus reflection coefficient. So here we have identified the reflection coefficient. Magnitude means only 0.45 you take. 0.45 whole square, 1 minus, multiply this, you will get your load power, the power delivered at load. Okay. Similarly, how we can identify the power at the input side? For that, the simple calculation is, we have a power relation half real of, or directly we can write average power is I square input square into Z in. Okay. I in means what? I in means this I naught, whatever the value we will get here. Square it, whatever the input impedance is there, solve it, or either you can directly take V naught into I naught divided by 2. It will be easy to understand. Half means it is average power. Okay. So here I will write half of V naught into I naught. V naught is the input current, input potential, and I naught is the input current. Multiply these two, you will get the input power. Okay. So like this, the many questions are there. Next class we will discuss more difficult question, and then we will complete this relation, and then we will go for the Smith chart, and we have one more important term called stub matching, which is the very more important chapter. Okay. Important topic, not chapter. Chapter is this one. So these are the certain relation. Next class we are going to discuss more difficult question with respect to 5 more questions, which will be a little bit complex to solve these numericals with respect to the transmission line. Okay. Thank you. One more information. I have uploaded the assignment questions in your Google Classroom. Your deadline is 14th. Today is 12th. 2 more days is left. Try to complete it, and within a stipulated time answer all those 5 questions and upload in the Google Classroom. Okay. Later on, if anybody fails to submit, no marks will be given to them. Okay. Thank you all.